Про технику это наука
о контактах, да, это именно так. Вот, поэтому, кстати, золото, да, на контактах ставят. Работаем? Okay, so let us recall what we were doing on previous class. Yeah, so we have Jordan decomposition. And this Jordan decomposition was for operator. Yeah, so suppose A was, so now I wish to take invertible matrix. So it is decomposed into two parts. So this is semi-simple. So that means that it has diagonal basis. Yeah? Matrix in some basis. So this is unipotent. Yeah, so and now we have proved that there exists polynomials P and Q, polynomials that such that P of A is equal to AS, and P of Q of A is equal to AU. And this tells us actually that AS and so in particular this also shows that AS and AU commute. And yeah, so this was what we know about Jordan decomposition for the operator. Yeah, so just I want to have some small remark. So remark. Yeah, and this decomposition is unique. Yeah, so this decomposition is unique. And with this property, because you can define semi-simple part intrinsically in terms of the space of eigenvectors and the space of just more general vectors, so just adjoint vectors. Yeah, so we can rewrite AS as a direct sum of the kernels of A minus lambda identity in some big power. So, what about, we can do the following remark. So suppose you have A and B commuting operators, such that A and B commute. Then you can ask about Jordan decomposition of A and B, and you notice that so you notice that since AS is just the polynomial of A, yes, so AS commute with B. And for the same reason, since BS is also P of P tilde of B for some other polynomials, so these are not, so these polynomials depend on A. So actually they depend, I would say they depend on the set of corresponding eigenvalues. Yeah, so the set of corresponding eigenvalues and how big are the cells. Yeah? So at least this polynomial. Yeah? So you see that this is BS for some other polynomial, so this implies that AS and BS commute. Yeah? Semi-simple. Yeah. They commute since the operators commute, yeah, because these are just polynomials of P and A and P tilde and of B. And the same thing for unipotent operators. The unipotent part, and so that they commute in just all of them, so are commute with each other. So if you want to write down AB, yeah, so it is of course AS, AU, BS, BU. And this can be written as AS, BS, and AU, BU. And so you see that, yeah, so at least what you can say, so that since these operators since these operators are commuting and unipotent, yes, so that then you see that AU times AU is also unipotent, yeah, because you have to write something like AU BU minus. So this is just yeah. So yeah. So notice that this is easier to speak about to derive this out of the following. I mean, it is not so easy to work with unipotent operators, but it is easier to work with nilpotent parts. Yeah, so let me put it like this. So let me just let me put it 1 plus n A, so which is nilpotent operator, and 1 plus n and b, yeah, and you see that since AU and BU commute, so and A and B commute, yeah, so that this implies that an A commute with NB. Yeah, so just because you are writing down NA as 1 minus NU. And this implies that you are writing down the operator in terms of NA plus NB plus NA times NB. And all these operators, they commute with each other. So they commute. So you use the fact that the sum of commuting nilpotent operators is nilpotent. Yeah? So if you have an A and B commuting nilpotent operators, so that NA plus NB is nilpotent, and NA times NB is nilpotent. And this, of course, implies that these operators are nilpotent. Yeah, so nilpotent.
You just used the decomposition into symbol and 1 plus nilpotent.
So here I just used that if this is unipotent, then this is nilpotent. Yeah? So, and if you want to say that, so since this commute, yeah, so you prove that BU commute with 1 minus AU, of course, yeah, and then you prove that 1 minus BU at the second step commutes with 1 minus AU. Yeah, so just of course, yeah, so of course I can rewrite this product minus 1 as some combination, but I mean it is easier to write it down like in terms of nilpotent operators, not in terms of 1 minus something. I mean just technically. And this yeah, so this shows that this operator is also unipotent. And notice that, yeah, so suppose you have, yeah, so here we shall need the following lemma that we shall need it for the further. So suppose you have collection of commuting operators. Suppose, so I'm not indexing them by the natural numbers. There could be infinite collection of operators. So, alpha act on the same vector space. And so you can just speak about so you can compose them, yeah, so only under these conditions. And so suppose that they're commuting, yeah, so just alpha L beta is equal to A beta A alpha. So and V is finite dimensional vector space. So finite dimensional vector space. Then I claim that the operators can be simultaneously trigonalized. Yeah? So then just A alpha can be, so you can choose the basis. So
and because the operators are same symbol removed, it be possible to diagonalize them?
Yes, but I want to have some additional remarks. So one can find the basis where A alpha are written in triangular form as triangular matrices. Yeah, so the form of, and if this operators so, and also you have additional remarks. So if you have, so you have many operators. Yes, so this large collection of the operators. Suppose you have the subset. So if you have collection of some just A gamma consists of semi-simple operators. So you can choose the basis in such a way that all operators are triangular, and these semi-simple operators are diagonal. Yeah? So then, additionally, we may assume that A gamma are diagonal. So this is somehow so that was mentioned that the operators can be so that the commuting semi-simple operators can be diagonalized simultaneously, but this lemma is a little bit stronger. It says that some of the operators can be, some part of them can be triagonalized, and some of them can be diagonalized. Yeah? So this implies, of course, so let us say about the corollary. Yeah, so if this semi-simple operators is also the product of semi-simple operators is also semi-simple. Yeah? And of course, this should be done I mean, in order to prove that if this is semi-simple and this is semi-simple, you should give the common basis where they are diagonal, and then the product will be diagonal. Yeah? So, this implies that we have already written AB as a product of semi-simple operator and unipotent.
Is it true that the semi-simplicity here is a property of the map between the groups? I mean that it doesn't короче, что это Жорданово разложение, но это то Жорданово разложение, которое для отображения групп, и тут как бы нету ничего, что опирается на Жорданово разложение в матрицах.
Не, наоборот, это вообще только про матрицы говорим. Сейчас мы говорим просто про матрицы. Да, ну как бы, но она имеет смысл, но только для групп, которые вложены в GLN. Да?
Сейчас только про матрицы.
Ну, сейчас, да, просто про набор матриц. Да? Мы говорим, ну, как бы и вот здесь я пока говорил только про набор матриц, ну, как бы но, в принципе, ну, сейчас мы еще поговорим еще раз про Жорданово разложение и увидим, ну, в смысле для групп, и увидим, что, ну, в общем, как бы, ну, вот те свойства, о которых я говорю, конечно, также следуют и для, ну, как бы, для Жорданово разложения для общих групп. So this is the semi-simple part, this is unipotent part. And so they commute, yes, so they commute. And this defines uniqueness. I don't remember that I have just really expressed. Yeah, so this implies that if you have these two operators, Yeah. So this implies by the so by the uniqueness of Jordan decomposition. Uniqueness of Jordan decomposition. This implies that this is precisely the semi-simple part of AB, and this is unipotent part of AB. Yeah, so let us discuss a little bit this lemma. It's usually, I mean, at least the second part with commuting operators should be well known to you. Yeah. And it will be convenient to reformulate what means trigonalization. What does it mean that we trigonalize the matrix? Yes, so notice that you can think of, so if you have the basis, so where the matrix is written in this form. Yeah. So you notice that if you take the linear combination of the linear span of E1, EI, yeah, so that just each EI is the linear combination of the previous one. A of EI is a linear combination of J, where J is less or equal to I. Yeah, so just Aij, Ej. So you see that this is a subset, clearly the subset of E1, etc., EI. And this suggests to introduce this is a VI, and to introduce the flag. Yeah, so the flag is just zero subspace. The linear span of E1, so the linear span of E1 and E2, etc. So where you stop at the vector space V. So you are calling this VIs, and yeah, so this is V1, V2, etc., Vn. And the condition is just that A of Vi sits inside Vi. So we say that A preserves the flag. Yeah, so we call such a sequence of subspaces a flag. Yeah. So so dimension of Vi is equal to I. We call just Vi sits in Vi plus 1. We call it flag, such collection of subspace. We call such collection of subsection of subspaces. A complete, actually, flag.
But I think that the upper triangles conserve a flag.
Preserve,
Preserves the flag.
yeah, so if the matrix, yeah, so and if the matrix is triangular, so it is if and only if it preserves the flag. Yeah, so it just A is can be written. So we say that A preserves the flag. We say that A preserves the flag if A VI sits inside VI. Yeah, and just the matrix is triangular if and only if it preserves the flag. Yeah? So A is triangular if it preserves the flag. Yeah, so a flag. I mean, you do not know which flag, yeah, but so some flag. Yeah? So some flag. So related with the basis where this matrix is triangular. And this is more or less evident. You just start picking. Yeah, so I mean, given the flag, it is only the part of the data. Just pick. So at each step, you have to construct the basis. Yes, so we reconstruct the basis EI by choosing EI inside the complement of VI minus VI minus 1. And it is clear, yeah, so, and what is the reason of speaking about the flag? So it's evident that the basis, when you're speaking about the basis, yes, so you can easily, so if the matrix is in the triangular basis, you can do the following. You can add to each EI the linear combination of previous vectors, and this will remain the matrix to be of the same form. Yes, so it will touch only, yes, so the corresponding elements that are upper than EI. So that means that still the basis is not chosen somehow canonical. And the flag also can, it can happen that, yeah, so the basis is not what is chosen canonical, but the flag depends on less options of the choice. Yeah? So of course it can happen that the matrix is diagonal and with different eigenvalues, then there is no problem to choose the flag. Otherwise, there is it can happen that there are different flags that so that there could be different choices of the basis. For example, for diagonal matrix, you can take for scalar matrix. Yes, so that consists of the same lambdas on the diagonal. You can take any basis, yes, so any flag. But the flag is more canonical than the basis. Yes, so the choice of the flag is more canonical than the basis. So our aim is to choose the flag. So in order to diagonalize all the matrices, so to diagonalize all matrices, one should take the invariant flag, so flag which is invariant with respect to all operators. And this is easy, yeah. So so it's I mean, but you have to just approach it in the right way. Yeah, so that, let me explain this. Yeah, so then you are doing the following. So you, yeah, so we do it by induction. So we construct the flag by induction. So we just find, I mean, so the first vector is just, you notice that the first element in the flag is just one eigenvector. So we have to find, so first we find the common, eigenvector to all of the operators for all A alpha. And it is done as follows. So you are, so you start by taking A. Yeah, so you take A for some operator. So you fix A, and